This presentation highlights why life data analysis may not be suitable for handling recurring data, which often arises in failure data obtained from CMMS utilized by maintenance organizations. It introduces a more suitable model to manage this type of dataset and discusses its advantages over life data analysis. In maintenance organizations, historical failure data obtained from CMMS forms the bedrock for reliability analysis. These datasets capture recurring events related to reparable assets. However, due to limited statistical understanding, life data analysis is often erroneously applied to these datasets. This presentation elucidates this misconception and introduces an alternative statistical model, recurring data analysis, designed specifically for such scenarios. LDA quantifies a population's reliability by fitting observed time-to-failure data to predefined distribution models. This method assumes the items are identical and operate independently, often abbreviated as IID, identical and independently distributed. This prerequisite implies the following requirements when applying LDA. 1. Each sample presents one observed value, either its age at failure or its current age while non-failed, and 2. Each time-to-failure data point must correspond to a distinct physical sample. Let's consider the failure data collected from a maintenance record, showing the failure instances of 3 pumps operating independently under similar stress conditions. Pump 1 has functioned for 3 years, while pumps 2 and 3 have each operated for 2 years. Beginner analysts often make the mistake of trying to fit a distribution to the time between failures across all systems. It's essential to recognize that the time between 2 failed items and the time to failure of an individual item are different. Why is this a mistake? The requirement IID data is essential in LDA. Each time-to-failure data point should directly relate to a distinct physical item. However, in this instance, the time between failures doesn't align with the time to failure of a physical item. If we want to apply LDA to the pumps, we're constrained to considering only the time to the first failure to uphold the IID requirement. Consequently, we're left with only 3 data points. Moreover, dealing with subsequent failures poses a challenge. Most failure history records obtained from CMMS or proprietary maintenance data logging systems often provide resolution details only up to the equipment level. Therefore, they primarily offer recurring information for analysis. As this type of data doesn't meet the IID requirement, using LDA for analysis becomes inappropriate. The followings are the likely information you would like to derive from your maintenance data. 1. Predicting the expected number of failures for a given period of time, considering the current age of the equipment. 2. Investigating whether there's statistical evidence indicating an increase in failure intensity, or decrease in mean time between failures over time. 3. If the mean time between failures is decreasing, what would be the optimal overhaul time? An alternate approach is required to model recurring data effectively, enabling us to tackle these inquiries. The non-homogeneous Poisson process with power law stands as the predominant reliability model for recurring data. This model encompasses the Poisson process and power law equations as shown here. The parameters lambda and beta within the equations are the model parameters to be determined. For this presentation, we utilized the recurring data analysis tool in Aero software to compute the model parameters lambda and beta. For a comprehensive understanding of the theory behind this analysis, consider exploring academic databases like PubMed, JSTOR, Google Scholar, or the IEEE Explore digital library. The recurring data is inputted into the RDA module of Aero software to compute the parameters. With the derived lambda and beta values, we proceed to generate the mean value function as demonstrated next. This is the mean value function, representing the cumulative number of failures plotted against time. It estimates the cumulative failures occurring over time t. By taking the derivative of this function, we obtain the failure intensity, demonstrated in the next step. Here is the failure intensity over time plot. Note that the failure intensity increases over time. Now that we have calculated the model parameters, let's address some queries concerning our reparable asset. For a new pump, what is the probability that there is no failure in 100 days? The software offers a user-friendly calculator dialog to access reliability data from the model. In this case, with the current age at 0 day and emission time of 100 days, the reliability stands at 91%. Next, how many failures are anticipated within the first 2 years? We can use the calculator to obtain this information. The prediction indicates approximately 3.9 failures within the initial 2-year operational period. If Pump 1 is currently 3 years old, what's the probability of it not failing within the next 30 days? Upon querying the model using the calculator, the reliability of Pump 1 operating for 30 days is estimated at 65%. As per the model's analysis, the pump exhibits a rising failure rate, implying a declining mean time between failures. Consequently, it seems plausible to anticipate the existence of an optimal overhaul interval for maintenance. Given an average repair cost of $10,000 and an overhaul cost of $50,000 for the pump, the question arises, when is the ideal time to conduct system overhauls? According to the calculator, the model indicates that the optimum overhaul interval stands at 891 days. RDA is a valuable method for characterizing equipment or subsystem failure rate behavior in the following scenarios. 1. Non-reparable component data collection is unavailable, making LDA impractical. 2. Collection of equipment failure modes down to component level is hindered by extensive effort. 3. Determining the optimal overhaul of reparable equipment is required. 4. Estimating the reliability of reparable equipment is necessary. 5. Forecasting the expected number of failures in a fleet of reparable systems is needed. This presentation emphasizes the limitations of life data analysis in managing recurring data commonly present in failure data from CMMS used by maintenance organizations. Recurring data analysis emerges as the preferred method in such cases, enabling examination of failure trends, conditional reliability, and determining optimal reparable system overhaul times. Additional articles regarding recurring data analysis can be found here. You can access the text-based article corresponding to this video via the provided link. Thank you for watching.